a Taylor series, and sometimes we call it a Maclaurin series. Because these are centered at 0. That's a special name for the series centered at 0. So we're going to come up with a generic process here to create a power series for any function. So let's consider the power series centered at 0. F of x equals the sum from n equals 0 to infinity of c sub n x sub n, where c sub n is just a constant. So those are just the coefficients of our polynomial. So let's use the summation notation and expand our function to see what the terms are. And we'll get, if I let n equals 0, I get c sub 0 because x to the 0 is 1, plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed plus c sub 4 x to the 4th plus dot 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 plus, and if I go to the nth term here, that would just be the c sub n x to the n plus dot dot dot. And so that is the polynomial, the infinite polynomial for our function. Now, it would be really nice if there was a way for us to figure out what the constant was. C sub 0, C sub 1, C sub 2, C sub 3, C sub 4. And if I wanted to find out what the constant C sub 0 was, since I'm centered at 0, if I found f of 0, if I let x equals 0, f of 0 here is going to be equal to c sub 0. And that would allow us to figure out what c sub 0 is. But let's figure out what c sub 1 could be. Well, in order to do that, you have to take the first derivative. So let's take the first derivative of our function. The derivative of c sub 0 is just 0 because it's a constant. The derivative of c sub 1x is just c sub 1 plus 2c sub 2x plus 3c sub 3x squared plus 4c sub 4x to the third plus dot 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 plus, and then let's take the derivative of our nth term, which would be n c sub n x to the n minus 1 plus dot dot dot. If we do the first derivative and we plug in 0, then we can figure out what c sub 1 was. And in order to find c sub 2, what we'll do is we'll take the second derivative. And to do that, you just take the derivative of c sub 1, which is 0. The derivative of 2c sub 2x is 2c sub 2. Plus, and then I'm going to multiply 3 times 2 to get 6. C sub 3 x to the first plus, 12. C sub 4 x to the second plus dot 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 plus, and the derivative of our nth term now is going to be n times n minus 1 times c sub n x to the n minus 2 plus dot dot dot. And I think we need to do a couple more iterations of this in order to be able to see the trend. So the third derivative will help us find c sub 3. So the derivative of 2c sub 2 is 0 plus the derivative of 6c sub 3x is 6c sub 3x plus 24 c sub 4x plus dot 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 plus, now let's take the derivative of our nth term. It'd be n times n minus 1 times n minus 2 c sub n x to the now n minus 3 plus dot dot dot. Fourth derivative is equal to 24 c sub 4 plus dot 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 plus. Now let's take the derivative of our nth term. That would be n times n minus 1 times n minus 2 times n minus 3 times c sub n x to the n minus 4 plus stuff. Now, I'm hoping that this is starting to look a little bit familiar here. This looks like the beginnings of a factorial. And just a reminder, a factorial, n factorial is equal to n times n minus 1 times n minus 2, and so on. Like 5 factorial is 5 times 4 times 3 times 2 times 1. So that's starting to look like a factorial. So we maybe can start to see the trend now. And in order to do this power series that's centered at 0, and we want to solve for c sub 0, c sub 1, c sub 2, so we would know what our polynomial actually is, let's plug in 0 and figure out what those constants are. So if I say f of 0, that means that all of the x terms in f of x are going to go to 0 except for c sub 0. And so I know that f of 0 is equal to c sub 0. And then similarly with f prime of x, if I go f prime of 0, I know that's going to equal, because all the x terms will go away except for c sub 1. And then f double prime of 0, everything will go away except for 2c sub 2. And then f triple prime of 0 will equal 6c sub 3. And the fourth derivative, evaluated at 0, will give me 24 c sub 4. And then I can do the generic here and say the nth derivative of f, evaluated at 0, will be, well, that's just going to be n factorial times c sub n. So what happens then if I take each one of these expressions here and solve for our constant? Well, clearly c sub 0 here equals f of 0. And then c sub 1 is equal to f prime of 0. C sub 2 is going to be equal to f double prime of 0 divided by 2. C sub 3 is going to equal f triple prime of 0 divided by 6. C sub 4 is going to equal f, the fourth derivative evaluated at 0, over 24. And then if we go down to find the generic c sub n term, well, that's just going to equal the nth derivative evaluated at 0 over n factorial. So now if we take all of these constants that we found and we substitute them back into our initial equation that we expanded for our polynomial, and I will rewrite that. And bring it down here. Here's our polynomial. So we're now going to take all of this information that we just gleaned as to what the constants equal, and we're going to plug it into our equation. But let's consider the following. 0 factorial is, by definition, and that's what the three lines mean here, instead of equals, by definition is equal to 1. So if you follow the trend, we can actually say that this is equal to f of 0 over 0 factorial. And then this would be f prime of 0 over 1 factorial. And so now we can write our polynomial using those terms. So I can say then that f of x is equal to, well, what was c sub 0? We said it was f of 0 over 0 factorial plus, and then c sub 1 was f prime of 0 over 1 factorial times x plus the third coefficient is going to be f double prime of 0 over 2 factorial times x squared plus the third term is going to be the third derivative evaluated at 0 over 3 factorial, because 3 factorial is 3 times 2, which is 6, times x to the third plus the fourth derivative evaluated at 0 over 4 factorial. 4 factorial is indeed 24 times x to the fourth plus plus, and then our nth term is going to be the nth derivative of f evaluated at 0 over n factorial times x to the n plus . So now, if we know the function, we can create our own polynomial for tailor-made almost for the f of x using a power series. All right? So I can write this in summation notation now and say n starts at 0 and goes to infinity. Using the nth term there at the end, I can say the nth term evaluated 0 over n factorial times x to the n is my power series. For my function f of x centered at x equals 0. Now what do we do if it's centered somewhere other than 0? Well, what we're going to do is we're going to use a transformation. And let's say we're centered at x equals a. So our power series is going to be the version of this where we say f of x equals f of a over 0 factorial plus f prime of a over 1 factorial times x minus a. And that's the transformation that we have to make when we're centered somewhere other than x equals 0. Plus f double prime of a over 2 factorial times x minus a to the second plus f triple prime evaluated at a over 3 factorial plus I'll do the nth term here. This will be the nth derivative evaluated at a over n factorial times x minus a to the n plus . And we can write it with summation notation, starting with n equals 0 to infinity, the nth derivative evaluated at a over n factorial times x minus a to the n. And that would be the power series represented for the Taylor series for a function centered at x equals a, which is different than x equals 0. All right, the Maclaurin series is for functions, that's a special name for functions that are centered, or Taylor series that are functions are centered at x equals 0. And this is just the general Taylor series. Both are Taylor series, it's just Maclaurin has a special name because it's centered at 0. All right, what I'd like to point out though is, believe it or not, we've been using Taylor series all the time, we just didn't know it. And this right here that I'm highlighting happens to be the equation of the tangent line. So if we use a Taylor polynomial, meaning we only use the first 2 terms of our power series for our function, then believe it or not, let's say we're centered at 0 here. Here's my function, and I'm centered at 0, and I want to show you that the first degree Taylor polynomial here is centered at 0, happens to be equal to the tangent line. So what does that mean if I were to use the first three terms? Well, now I have a parabola that is going to fit this function at the point of tangency, maybe a little bit better. So you might have a tangent parabola. If you use 4 terms, you might have a tangent cubic, or you will have a tangent cubic. And then you can see the power, pardon the pun, of this methodology here is that the tangent line is a good approximation for your function value when you're close to the point of tangency. But if you increase the number of terms that you use in this power series, your estimation or your approximation for the function value gets even better in the neighborhood here because it's a closer and closer fit to the function over its quote-unquote interval of convergence. All right, so let's do an example of this so that you will understand why on earth we're doing this. So the first thing we're going to do is construct, construct a power series for f of x equals e to the x centered at x equals 0. All right, so what I do first, always, is to write down the generic function, and I saved it, so we have it here. Well, let's get rid of this piece because that's not helpful. I wanted to use the other piece, which is right here. Now let's see if they'll let me copy this. Let's try it. Oh well, I'll just write it out again. All right, that's like plans. So f of x is going to equal, the generic form is going to be f of 0 over 0 factorial plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial plus, times x to the third plus, plus, we can say n derivative evaluated at 0 over n factorial plus, times x to the n plus, So now, in order to construct a power series for e to the x, what we have to do is find out what the coefficients are. And in order to find the coefficients, we have to take multiple derivatives. So f of x is equal to e to the x. And I started off with an easy one this time. F prime of x is equal to, well, e to the x, which is nice. F double prime of x is equal to e to the x. F triple prime of x is equal to e to the x. The fourth derivative of x is equal to e to the x. All right? And let's go to f of 0. We can see f of 0. Well, when you plug 0 into f, you just get e to the 0, which is 1. F prime of 0, which is nice, is also 1. F double prime of 0 is 1. F triple prime of 0 is 1. And the fourth derivative of 0 is equal to 1. All right, so let's use this information and plug in to our generic function up here. And we can say f of x is equal to, using all that info, this will be f of 0 over 0 factorial is just 1, plus f of 0, f prime of 0 over 1 factorial is just going to be 1 times x, plus f double prime of 0 is 1, so it's going to be x squared over 2 factorial, plus, let's plug in f triple prime of 0, which is 1 over 3 factorial, so that would just be x to the third over 3 factorial. Plus, we could say x to the fourth over 4 factorial. I hope you now see the pattern. Plus This would be x to the n over n factorial plus dot, dot, dot. All right, so now we've got our Maclaurin or Taylor series centered at 0 for, remember now that this is equal to e to the x over whatever interval of convergence, what the interval of convergence might be. So let's write this in summation notation, starting at n equals 0 to infinity. That would be x to the n over n factorial. Now, in order to see if this works, all of this madness, let's go to Desmos and type in what we know. All right, so going to Desmos, let's type in y equals e to the x. There it is in all its glory. And then let's type in our Taylor series. So we're going to say y equals, and I'm going to go to functions over here and find the miscellaneous and put my sum here from n equals 0. And I'm going to use a slider here, k, and we said that was x to the n, and I want to insert the slider, divided by n factorial. All right, so what happens, do you see, when k is 1 and I have only one term in my equation there? What happens is that I have the tangent line. So that means that we've been working with this all the time. So I'm going to get a new snippet here and suggest to you that the Taylor series, the Taylor polynomial, that's only 1 degree, is equal to the tangent line. That's what k equals 1. So what happens, do you suppose, if we let k equal 2? We just go up by 1. And that you see now that that is a tangent parabola. So I'm going to snip that. So that polynomial is a degree 2. And you'll see that it's a nicer fit here for a larger portion of the function e to the x. All right, moving right along, we can try k equals 3. And there is the tangent cubic. So the Taylor polynomial that's a 3rd degree here fits even better and is a better estimation for the function over its interval of convergence. All right, so that's the 3rd degree. And the 4th degree is going to look even better. It's like we're creating a polynomial function to tailor-made to fit this function. So I'm going to adjust this so that our k starts at 1, and let's go to 100 and have our steps be in increments of 1. All right, and I'm going to zoom out here so you can see what happens as we increase k. What happens is we keep getting polynomials here, and what's happening to the interval of convergence? Well, gosh, it seems to be getting bigger and bigger and bigger. And believe it or not, the interval of convergence, if you use an infinite number of terms here, is going to be negative infinity to infinity. So this converges for all real numbers. That's pretty amazing. So where we see e to the x, we can dutifully replace it with 100% accuracy with the Taylor polynomial, or the Taylor series that we created. Right here. That is definitely e to the x, or an IOC, the interval of convergence from negative infinity to infinity. Which is pretty amazing that you can replace a function with a series of, or a polynomial, an infinitely many terms polynomial. All right, and so that is how you create a Taylor polynomial.